Okay. So in last video we have demonstrated how this minimum Hamming distance is helping us to find out errors at receiver side, and the relation between number of errors to be caught and the minimum Hamming distance. If minimum Hamming distance is, let us say, if you have a minimum Hamming distance as 2, then it is possible to detect only one error in that coding method. Similarly, we have given in case of error correction, the minimum Hamming distance to be maintained is it is 2t plus 1, where t is number of errors to be detected, number of errors to be detected. So likewise, there exists some relation between minimum Hamming distance and number of errors to be detected or corrected. Okay, and today in this video we talk about one more method of coding the code words, that is linear block coding. In linear block coding, the principle of this linear block coding is most of the block codes we have used today are comes under linear block codes only. So that's what we have discussed in previous lectures. We come across block coding where message is divided into equal size of data units of size k bits each, and then redundant bits are added and code words are prepared. This is what we have seen in previous methodologies, and all these block codes are comes under a subcategory called linear block codes. Linear block codes. Now, there is a property for linear block codes. The property is when you take any two code words, and if you perform XOR on it, the result should be one more valid code word. I repeat. So, see here in this definition itself, you can understand a linear block code is a code in which the exclusive OR of two valid code words creates another valid code word. Means if you have 4 valid code words, now what I do is I take 2 and perform XOR. That XOR will result in any of the remaining 2, So this way, if the property is held in that code words, then that code word you can call it as linear block coding. So that is a basic definition, and according to these principles, that code words are created. So we will see that in next slides. Okay. Let us consider this example. This is what we are discussing in first block coding techniques. We have a data word of 2 bits, and we are making it to 3-bit data code word by adding one redundant bit. So now let us observe whether it is comes under linear coding or not. So in order to become linear coding, it should hold a principle of by XORing any 2 valid code words, it should result in the third one. So let us look whether it is working or not. So we have these code words like 00011 and 101110. These are the code words according to these data words. Now what I do is I take any two. Let us say in this example I have taken first one and second one. 000 followed by 000 is first valid code word, and 011 is another valid code word. Now what I am doing is I am taking those two and performing XOR operation on it. Take 000 and 011 and perform XOR on it. When you when you perform XOR on it, then the principle of XOR, as you know already. So if 2 bits are same, the result is 0. If 2 bits are different, then the result is 1. It is to identify difference between the bits. Very simple. It is to identify difference between the bits. If 2 bits are differ, the result is 1, and the 2 bits are same, maybe 0 or maybe 1, the result is 0. Okay, this way, if you observe 0 the answer is 0, 1 differ 1, 1 differ 1. So now we got a result as 011. Now let us check this 011 is present in the resultant valid code word set or not. This is a valid code word set. Total we have four valid code words, and we have taken 2 valid code words, performed XOR, and the result is 011, and that is present in the, if you take this one 011, is it a valid code word? 011 is already there. 011 is already there. That is second one itself. So this way, we can conclude that whatever the coding is applied in this method is a linear coding. So that's the principle of linear coding. So it should make a maintain a principle of XORing any two valid code words must result in the one more valid code word which is present in that table. So if it is not so, then it is not holding that principle. So it is the case for a code word of size 3, right? So let us look into one more where we will see that second table code word with 5 bits. So now, so in this slide, now we are making use of more redundant bits, that is three redundant bits, and data bit is of size 2, and finally the code bit becomes 5 bit size. Now what we will do is we will take randomly any two. Let us say second one and third one is taken. And we started doing XOR on it. So now first two bits differ, the result is 1, and again 1 0, the result is 1, 0 1, the result is 1, 1 0, the result is 1, and 1 1, the result is 0. Now we got a result of 4 ones followed by 0. Now if you got a result and whether it is present in the valid code word set or not, we will check. So when you observe this 4 ones followed by 0, it is already present in the valid code word list, that is this one, 1 1 0, 1 1 1 0. So that we can conclude that our second methodology what we have adapted so far, like code word of size 5, are also maintaining this property called as linear block property. So this way we can define this linear blocking, and now we will see one of the example of linear coding, right? So the simple example here is a simple parity check code. So this is one of the linear code. Now what we are trying to do is here we focus on how these redundant bits are created. Is our focus in this method. That's what our coding techniques will suggest us. Now, when you take a word, data word, only one bit redundancy is added in parity check. In parity check, only one bit redundancy is added. There are two kinds of parities. Even parity coding is there and odd parity coding is there. So, if a code word maintains even number of ones, if a code word in the sense data which is added with redundant bits. When code word maintains even number of ones, then we call it as even parity. When code word maintains odd number of ones, we call it as odd parity. How this even and odd numbers are maintained means by adding one bit to the data word. For example, if data is having 3 ones inside it, then in order to, if you are following a method called even parity code, in order to make it as even, redundant bit is set to 1 because already data is having 3 ones. So now redundant bit is set to 1, so the total number of ones in that code word becomes even. So even parity, that we call it as even parity. For example, if you are going with odd parity logic, if data word consisting of 3 ones, then the parity is set to 0 because total number of ones in the code word must be equal to odd in case of odd parity. Most of the time in our examples, we make use of only even parity. So the methodology he is explained with this diagram. When you have it is also known as vertical redundancy check. So parity, simple parity check, also known as vertical redundancy check. Generally it is used to detect 1 bit errors. Simple parity check is used to detect 1 bit error, or we call it as odd bit error. Odd bit errors means 1 bit error we can caught, 3 bit error we can caught, 5 bit errors we can caught, but we failed to caught even number of errors, even bit errors. Like if 2 bits are corrupted, this method may not work. If it works for error detection when there are odd number of bits corrupted, 1, 3, 5, 7 likewise. So we will see those examples in next slides. So as of now you remember how this methodology is working. So when data is there with a content of 1 1 4 zeros by 1, this is what our data is. Now the generator job is to add redundant bits. How redundant bits are added means based on the number of ones present in the data. So now in this example they are making use of a even parity concept. So here you got only even number of ones, 1, 2 and 3. So we got only 3 ones. And code word should have how many number of ones? In even parity it should have even number. So in order to make it as even, so one additional bit is added, that is this one. Vertical redundancy check or parity check will add 1, and now total number of ones in this code word becomes even. Now at receiver side the logic is very simple. So if the received code word is having even number of ones, nothing is wrong. If received code word is having even number of ones inside it, nothing is wrong, and you simply conclude that no error is detected. So no errors are there in the transmission, it is a correct data. This way the receiver is having a job of counting number of ones and the sender is having a job of counting number of ones. In order to make it as even, maybe redundant bit is set to 0 or 1, depends on the count of ones present in the data unit. So in this case the redundant bit is set to 1 in order to make all the ones in that code word to be even. So this way this simple parity check method will work. Now we will see one example how it is going to work. And now the problem we need to identify. The problem is what? It is not, if there is only one bit error, definitely at receiver side the count is changed. Very simple, the count is changed to odd. When count is changed to odd, the receiver is not capable of, when it is odd, receiver is capable of saying that there is an error. But whenever it is even, then we think that the data is not corrupted, the code word is not corrupted. But what happens means, for example, I have sent a code word with 4 ones inside it. I have sent a code word with 4 ones inside it, but during the transmission multiple bits are get affected. Like number of ones in that code word is 2 now. As per the logic of this receiver concern, receiver always checking for what? Even number of ones are present or not. If even number of ones are present, consider it as correct one, and if odd number of ones are there in the received code word, consider it as a corrupted one. So this is the logic. This simple logic may not work for detecting even number of errors. That's what we are trying to project here. So the problem with this parity is it can detect only odd number of errors. Odd number of errors in the sense, let us say we have sent we have sent a code word with 4 ones. If 1 is corrupted, the count becomes even. If two bits are corrupted, the count of ones becomes even, so it is not detectable. If 3 bits are corrupted, let us say we have sent 4 ones, 3 are corrupted. If 3 are corrupted, the remaining is what? 1. 1 is a odd number. So whenever you got a count of odd at the receiver, definitely receiver thinks that there is an error. There is an error in that data transmission. So we conclude that the simple parity check method will work for detecting only odd bit errors. Only odd bit errors means 1 bit error, 3 bit error, 5 bit error, because then only we can differentiate which is even number and which is odd number. So if 2 bits are subtracted from 4, still it is even number. So that's the reason even number of bit corruptions are not detected by this method. So now let us look into one example. So here a letter A is transmitted. The ASCII value of A is 65. That 65 binary value is 1 5 zeros followed by 1 0. So this is what code belongs to capital A. Now whenever it is transmitted like a code word, so total number of ones present in this A is 2. So parity bit is set to 0. Parity bit is set to 0 so that it is transmitted. Whenever it is transmitted in the air or in the transmission media, then the receiver is going to check how many number of ones are there. Let us say there are 2 ones. When there are even number of ones, so it thinks that there is no error at all. So we have received very good content. There is no error in the content sent by the sender. But unfortunately in this second methodology, see this. Here also, whatever we have sent is A, capital A, which is 1 00000110. This is the code for ASCII value 65. So now unfortunately what happened means, during the data transmission 2 bits are corrupted. 2 bits means one is part of the data, one is part of the parity bit itself. There is a scope to corrupt this parity bit also. So when parity bit is corrupted, so it becomes 1, and one of the content is changed. Now what happens means this value is corresponding to which character? Q character. Now if you count to the number of ones in this code word, it is even. Whenever it is even, it doesn't understand, the receiver doesn't understand how many number of even ones we should have. It knows only one thing: if a received code word contains even number of ones, accept it; if it is odd, reject it. So now what happens means, we have sent A, but in the transmission 2 bits are corrupted, it becomes Q. So capital A you have sent, but the receiver unable to detect its 2-bit errors, and finally he accepts Q. So you said A, actually we said A at sender, but it is received like a Q at a receiver. So this type of errors are never caught in single bit, simple parity methods or simple parity code method. So you can understand from this slide, only the errors caught by this methodology is even number of bit corruptions like 1, 3, 5, 7 likewise. So this is about a simple parity, which is only working for detecting odd parity changes. Even parity changes never be detected. Okay, right. So let us see this one. It is one more example where you have data words of size 4 and the code word of size 5. So one redundant bit is added. Now in this, generally the notation of any coding is like this. C means coding of two numbers. The first number indicates n, means size of the code word. Second number indicates size of the data word. This is a representation of any coding technique we take. In linear coding or block coding, the coding is represented with two parameters. One is n, which is number of bits in the code word, and second parameter is k, which indicates number of bits in the data. The difference between these two is called as redundant bits. How many number of redundant bits are existed in this code? So if you observe, the number of redundant bits existed in this methodology is what? Only one. Only one. So now here also you can check, this is also one of the linear code. Now whenever you take any two code words, do the XOR, and definitely the result must present in the same table of valid code words. So that's the reason it is one of the linear coding technique. Linear coding, simple parity check comes under linear coding technique, and it still holds the principle of XORing any two valid code words, which results in one more valid code word. It may be same also sometimes, means whenever you do XOR with this one and second one, the result is this one only. So it need not to be like when you do XOR on two valid code words, it must result in other, not like that. It must result in a valid code word. It may be same one what we have taken for the calculation, or it may be different from the one we have taken. Okay, it may be present in the table. Finally, it must be present in the table as part of your parameters taken for the XOR, or it may be other one. It should be in the valid code word list. This way, the principle of linearity is working for simple parity check code, which is a combination of 5, 4 in this method. See, 5, 4. So now let us conclude this simple parity check code. The main purpose of this simple parity check code is to detect the errors. That is, it is not for error correction. Remember, this method is only there to detect the errors. Okay, and immediately we have a question, that is, how many number of bit errors it is going to detect. Is it going to detect 1 bit errors or more than 1 bit error? So it is going to detect more than 1 bit error, but the number of bits corrupted must be equivalent to odd number. Then only it is able to detect the errors, otherwise no. Okay. Now here in this parity, we have a data word of k, and we are converting that one into n-bit code word. And how many number of redundant bits are used in parity check means only one. So that is to indicate whether the count of ones in the data word becomes even or odd. So 1 bit is enough as a redundant bit. So that's the reason n becomes k plus 1. 1 is the redundant bit, k is the number of bits present in the data unit. So now the minimum Hamming distance maintained by simple parity check is d mean. So d mean in the sense minimum Hamming distance is equal to 2, which means it is going to detect single bit errors. It is going to detect single bit errors. Single bit errors at multiple places. That's okay. Single bit errors. And there is one more, that extra bit we call it as parity bit, and it is also known as VRC, vertical redundancy check, that we have already covered. And now the parity bit is selected in such a way that the total number of ones in the code word becomes even or odd. That depends on the parity code we use. If you are using even parity, select parity in such a way that total number of ones in the code word must be even. And if you are using odd parity, the total number of ones in the code word must be odd. So this is a simple brief about simple parity check code. So this way it is working for only error detection, that too odd bit errors only caught. Now, so working principle of this one, like a structure of this one. So when you talk about this structure of encoder and decoder, whatever it may be the method, there should be a generator program, there should be a checker program. So in case of this sender program, encoder is there and taking data as an input, and that data is given to the generator, and generator is going to produce redundance bit. How many redundance bits are created in simple parity? Means only one. So that is added or not. So now A32 or not is called as code word, that is sent through the unreliable transmission medium. So whenever it is received at this side, so now we have received the content Q0, B0, B1, B2, B3. So simply what we are taking means this content is treated as B3, B2, B1, B0, Q0. So whatever we received is may not equal to the same whatever we have sent. Now we need to check whether it is corrupted one or corrupted one. Okay. So in order to check it, the checker program job is, he will take the input, that is whatever the data bits are there, that is in this case it is B3 to B0 taken, and parity bit also taken. Now total number of ones in the code word is what? Even. If it want to be error free, it should be even. So when even number of ones are added, the answer is 0. As per the XOR logic concern modulo arithmetic, when even number of ones are added, the answer is 0. So now when checker get a answer of 0, that we call it as a syndrome. Syndrome means by adding all the bits in the code word, all the bits. But if you observe here, we take only 4 bits and encoder, those are taken, and generator will identify whether all are even or not. If all are even, then 0 is added. If all are odd, count is odd, then 1 is added. But in this case, the syndrome value, whatever calculated from the 5 bits, B3 to B0 and Q0, by adding all these things, if you get 0, meaning of that one is total number of ones present in the code word is even. So when it is 0, accept it. Decision logic is what? Based on the syndrome value, it is going to take a decision whether to discard it or accept it. So as it in error detection methodology, it is having 2 options at the checker. You may reject it or you may accept it. So now if it is equal to 0, if syndrome value is equal to 0, accepted, and we are getting back our data, that is what? Sent, that is A0 to A3, we get back our data. And if there is any change in the syndrome, then definitely we are going to discard it, saying that there is an error in the received code word. So this is a function of encoder and decoder in simple parity check method, simple parity check coding. Okay. So these are the activities which are taken place at sender and receiver. So now at sender side, what it is going to do is, the parity is calculated. How parity is calculated from equation means, parity is calculated by adding the data bits, very simple. So what is our data? A0 to A3 is our data. So in order to calculate parity bit, add all by using modulo 2. When you add all these things by using modulo 2, now what you will get is, you will get R0 as 1 when already you have even number of ones. When you have even number of ones, the redundant bit is 0, right? So the number of ones is even, then the result is 0. If A0 to A3, is already having even number of ones, addition always leads to 0, right? So when you got the result, whatever the result you take, if all are having even number of ones in the data, then R0 is 0. If all odd, let us say you got 3 ones in the data, 1 1 becomes 0, and 0 1 becomes 1. So now whenever we got a even number of ones, you are going to get a 1 as a parity check, parity bit. So this way parity bit is calculated at the sender. So sender job is simple job, add the bits, add the data bits. If you get a result of 0, then already the data word is having even number of ones. If data word is having odd number of ones, we get parity as 1. So this way the work is taken place at the sender. And if you consider this side, receiver side, in receiver side, what he is going to do, only he also does the same thing like adding only, but how many number of bits are added? The number of bits are added at receiver is 5, because we have sent code word as what, 5-bit code word, which includes redundant bit also. So now by adding all the bits like B0, B1, B2. See, in this slide it is not given, it is taken from the above, so it is not like that. Here B's are there, and which is added with the redundant bit. All 5 bits are added in this case. At receiver side, you remember, all 5 bits are added, and if the 5 bits results in 0, no error, and if it results in 1, there is an error in the received code word. Try to remember. So don't confuse with this notation. This is not right. So we need to consider previous one only. So what are added to get the syndrome means S0 is equivalent to B3, B2, B1, B0 and Q0. So these are the values added in order to get your S0, which is syndrome. And if syndrome value is 0, no errors are detected. If syndrome value is 1, the received code word is wrong. This is what the action taken place at the receiver side. Okay, let us take one example how it works. We have some transmission scenario. Assume that sender sends a code word 1011, and the code word created for 1011 is what? 10111, because the total number of ones present in this data word is 3 and the redundant bit becomes 1. So this is what the sender will send. And now observe the cases. If no error is there, the received code word is same, and what happens when syndrome is calculated to 0 by adding all the bits. Like how many bits are there in this received code word? 4. When you add even number of ones, then you get an answer of 0. So when you got 0 as a syndrome, we treat that the redundant bit is removed, that is last one is removed, and you got your original data 1011. That is very general case if there is no error at all. So that is first case. And if you take second case, one bit is corrupted. Let us say one bit is corrupted, that is A1 bit. A1 bit in the sense, if you observe here, the code word becomes what? 10011. So if you observe that A1 bit in the sense from left. So if you observe here, this last one is redundant bit, this is A0 and this is A1. So this bit is corrupted to 0. So now it becomes what? 10, it becomes 10011. Now when you have a code word with even number of odd number of ones, the syndrome value is 1. When you have a syndrome value of 1, then no data word is created, because when there is a syndrome value as non-zero, then we simply reject it. So that's the reason no data word is created at the receiver. So hope you understood this second case. In second case, one bit is get changed. If one bit is get changed, then you are going to get a syndrome value as 1. When syndrome value is 1, then the data word is not created and simply rejected. Received one is rejected. Now you take one more. This time again single bit error, but it is in the place of redundant bit. It is in the place of redundant bit. So now if you observe in this case, third case, one bit is changed. Which bit is changed? Or not. Or not means last one in the received word. Or not is changed. That is 1011, 0 now. Actually it is 1, it is 0 now. Now if you take the count of ones are what? Odd. When it is odd, the syndrome value becomes 1 and no data word is created. So we need to observe one point at this third statement. The point is there is no change in the data. The data is correct. Whatever the data we have sent is 1011, but the data changed is part of the redundant bit. So when redundant bit is changed, that also leads to identification of the error. So though you have received your data properly, but because of the corruption in the redundant bit, again it is making syndrome value as 1. syndrome value as 1. So the received code word is simply rejected. So this is third case, right? So now we have one more case, fourth case. Now an error changes or not, and second error changes A3. Now how many bits are changed? 2 bits are changed. So when 2 bits are changed, the content becomes 00110. 2 bits are changed. 2 bits. Previously 2 ones are there in our message. Now it is changing 2 ones to 0. 2 ones to 0. Now the received code word is 00110. Now when you count number of ones, it is even. It is even. So the syndrome value is 0, and what word is created from it? The redundant bit is 0. So this is redundant bit. So remove it and you got a word of 011. So this is created at the receiver side. But it is not the one which is sent by the sender. So the sent one is what? The sent one is 1011. But unfortunately, because of 2 bits corrupted, we are getting syndrome as 0, and we are recovering our data by removing the redundant bit. Then you will get a data word of 011, but it is not the one sent by the sender. This way, wrongly, the receiver is going to create a data word which is not sent. So this is a problem with the methodology. This is a problem with. But if you go with third one, last case, 3 bits are changed. So now if you observe in this case, A3, A2, A1 all are changed. Now the received code word becomes the received code word which is like 01011. So the syndrome value is 0. When syndrome value is 0, the data word is not correct, but it is going to do the checking, guarantees that only single bit errors can be caught. Odd number of errors. So it is going to find out odd number of errors means if you change, see in this case, A1, A2, A3, these are the 3 bits changed to by errors, and the received code word becomes 01011, A1, A2, A3, A1, A2, A3. These are the changes. And syndrome value, when syndrome value becomes 1, the data word is not created, because syndrome value always 1 leads to rejection. So it shows that it is going to, the simple parity check will guarantee to detect one single bit error. Can also find any odd number of errors. Odd number of errors in the sense, the total number of ones should become 1 at the receiver, odd at the receiver, such kind of errors. Sometimes what happens means, what it is going to do is, it is going to change 10 to 1 and another 1 to 0. Likewise, it is going to have some combinations, and finally it leads to syndrome value as 1 at the other side. So this way, when syndrome is calculated to 1, and when even number of ones are there at the receiver, even number of ones are there at the receiver, even number of changes are there at the receiver sender side, and it is caught by the receiver, then it is unable to detect. So only this method will detect odd bit errors. Only this method will detect odd bit errors. So this way we can conclude this method. So that's what the conclusion for this one. A simple parity check code will detect only odd number of bits, odd number of errors. Because when odd number of bits are changed, then only it is possible to find we got even number of ones or not. So when you have even numbers, subtracting one even number from another even number leads to even number only. That's the reason it is unable to detect errors at the receiver side. But if you subtract odd from the even, then the result is odd. When the result is odd at the receiver, it is considered as a error. It is considered as an error. So that's it for this video. So in next video we talk about one more method, that is to detect more than 3-bit error, more than 2-bit and 3-bit errors with the help of same logic called parity check. But in this case we make use of a methodology called matrix form. So the data is represented in matrix form. Instead of calculating 1-bit error, one parity check, we calculate more than 1 parity check, that is for each and every row. So that we will see in next video, and along with that Hamming code. Those two we will cover in next video.